Next, we'll put the car rig into the shot file. Let's see how to connect the car to the motion curve and do some corresponding settings at the same time. Let's look at my scene. I have a ground model here. It has some bumps on it. There is a motion curve I drew, and a reference car rig. First, let's see how to put the car onto the motion curve and make it move along the curve. Let's hide the ground model for now. To make a node move along a curve, Maya actually already provides us with a solution. Let's do it together. We create a locator. Let's call this locator car pose. Then select this locator and shift select the NURBS curve. Then, in the constraint menu, find motion path, attach to motion path, click it. Let's increase the local scale of its shape node a bit, so we can find it easier in the scene. This way, we'll see this locator has been snapped to one end of the curve, and as we scrub the timeline, it will move to the other end of the curve. If we look at the nodes, there is a node called motion path. This motion path node has two keyframes. At frame 1, it is 0 here. At frame 120, it is 1. So it's a value change from 0 to 1. If we delete its keyframes, right-click Break Connections, we can manually adjust it again ourselves. For example, let's change it to 1000 frames. Then set it to 0 at the first frame. Right-click Key Selected to add a keyframe. Then at frame 1000, set it to 1. Right-click Key Selected again to add another keyframe. This way, see, it will move from one end to the other, and the time it takes is 1000 frames. Next, let's look at the motion path settings. Select the locator, Ctrl+A to switch to the attribute editor. Find motion path 1 in the tabs. Here we'll see it has some attributes, like word.type, word.vector. We should be familiar with these attributes. They look very similar to the aim constraint we discussed before. Actually, making a node move along a curve, its idea is very similar to an aim constraint. The position is extracting the curve shape's position information, then remapping from 0 to 1 onto the curve's length. The rotation is actually based on the aim constraint concept. Forward is using the curve's tangent direction as the aim vector. For the up vector direction, there are several options here. We can use object up, we can use object rotation up or scene up, or we can set a vector direction ourselves. Here, let's simply set it to scene up, using the world y-axis direction as a reference. Then we can look at its front axis. This is actually the aim vector mentioned in the aim constraint. Here, the default is x. We know the car faces forward along the z-axis. So to keep it consistent with our car's default direction, we need to change this to the z-axis. This way we have a locator with y up and z forward. When we turn corners, we'll see that too. After setting it up, we now need to start thinking about how to connect the car to this locator. First, let's snap the word controller over. Select our controller. Select the locator. Then in Modify, find Match All Transforms. Match both translation and rotation. This way we'll place the car in the initial position. Next, select the locator. Select the cog controller. Then do a parent constraint. Note here, we must check Maintain Offset. Otherwise, the cog controller will be snapped to the locator's position. This way, let's look again. It will move along our curve. So our first effect, making the car move along the curve, is done. What do we need to do next? Next, let's see how to connect the auto wheel rotation with the car's movement. Here we know that for auto wheel rotation, we need to know how much distance the car has actually moved. So how do we get this value? Actually, this is very simple. Look at our locator. Its motion path node has an attribute called u-value. U-value ranges from 0 to 1. When moved to any position, it will be a value within the range of 0 to 1. This value is actually what percentage it has moved along the curve. Now it has moved 0.323. If we can get the actual length of the curve and multiply it by this u-value, won't we get the distance the car has moved? For example, if the curve length is 100 and we are at 0.323, then the car's travel distance is 32.3. If we go back a bit, Now it's 0.096. Then the car's travel distance should be 9.6. So how do we get the actual length of the curve? Here, let's select the curve first. Enter the node editor. Add it in. Here is the curve's shape node. We need to create a new node. This node is called curve info. Let's rename it, call it curve length. What is this curve info node used for? It is used to extract the curve's shape information. Here, we connect the wall space attribute of the curve's shape node to its input curve. Then let's look at the attribute editor. We will see an attribute called arc length. This is a curve's length information. Next, we need to find the motion path node. Because we want to multiply the u value with the curve length, click motion path in the attribute editor tab. Then in edit, find select node. Add it in as well. Next, we create a mode double linear node. Connect the arc length attribute. Then connect the motion path u value. This way, the result of the multiplication is the distance the car has currently traveled. Let's connect it to the cow controller. Connect it to this distance attribute. Let's take a look. We'll see our wheels now have a rotation effect. Clear the node editor and close it. Okay, so this way, our second step, making the wheels have an automatic rotation effect while moving forward, is done. What do we need to do next? There is still a problem here. When the car turns a corner, we'll see the car is turning as a whole. But we know this effect is incorrect, because there is a steering controller here. When the car wants to turn, the wheels should rotate first and then lead the car into the turn. So how do we do this? We briefly mentioned this before when setting up the steering. There is an aim constraint controller here. When making the car move along the curve, we need to create another locator. Ensure it stays in front of the car's own locator. This way, it can always have a steering effect. For example, it's here now. If we set a locator in front to constrain this controller, the controller will be in this position. Look, at this time, the car already has a steering effect. Let's do it. The method here is the same as before. We create a locator. Let's rename this locator. Call it car turning impulse. Then connect it to the curve as well. In constraint, find motion path, attach to motion path. Here we delete the keyframes for the u value. Then if I set a value, for example 0.05, and scale its shape up a bit, we will see it will be in front of the car. But I don't want to set any animation keyframes for it anymore. Because for the animator, they might adjust the car locator's u value based on the shot's effect to decide how much the car actually moves forward or backward during a certain period. At this time, we want this front steering locator to always stay in front of the car. But if we have to set keyframes for it too, then the animator has two attributes to adjust. That would increase the workload, and it's very unnecessary. Because we know this locator just needs to stay ahead of the locator representing the car itself. So here, we can actually use the car locator's u value plus a value. This ensures it's always in front of the car. Let's do this here. Select the car's locator. Find the motion path node. Select it. Then enter the node editor. Add it in. Then select the motion path node of the newly created steering locator and add it to the node editor as well. This is very simple. We create an add double linear node. Then connect the car's motion path u value over. Connect to the add double linear. Then add a value on the other side, for example 0.05. We can adjust this value based on the result later. Then connect it to the u value on the other side. Let's see. 0.05 is obviously a bit too far forward. Let's change it, like 0.02. We find 0.02 is a bit too close. Let's change it to say 0.03. Okay, 0.03 looks pretty good. So we confirm this locator is at the 0.03 position. Clear the node editor, close the node editor. This way, when the car moves, this locator will always stay in front of the car. But there's still a problem here. When the car moves to the very end, because the car's value is from 0 to 1, when it moves to the very last point, the forward locator has no room to go further forward. So here we leave some space at the end for the car's locator. We change the maximum value to 0.97, because the distance between them is 0.03. Then right-click to set a keyframe. This way, see at the end, it will stop at a position slightly further back, letting the steering locator reach the end of the curve. Next, we use this newly created locator and our previous steering controller to do a parent constraint. This way, see, when the car reaches certain positions, the wheels will have a steering effect. With this, our third step is done. What do we do next? There's one thing about the steering I'm still not satisfied with. Look, like here there is a very sharp turn. In this situation, you'll see the car's wheels here turn to a very extreme angle. This angle looks very unrealistic, because a real car shouldn't be able to turn to such a large angle. We mentioned when discussing steering rigging before, the general wheel steering angle is roughly between 30 and 40 degrees. Some might reach 45 degrees. But it certainly won't be a large value approaching 90 degrees. So generally when this happens, what occurs? The car will have a tail sliding effect. It will drift. So here, because the wheel rotation angle is too large, let's make a drift effect like this. Because we don't want the animator to have to manually set this effect for the front controller every time. We can make it more automated. So how do we do it? What do we need first here? First, we need the angle when steering. Let's take a look. Let's see how many degrees it has turned. It has turned 48.78, about 49 to 50 degrees, obviously exceeding the maximum angle the wheels can rotate. We can't use this value directly, because this value will change. Our steering controller is a child of the back controller, and the back controller is a child of our front controller. At this time, if we rotate the front controller to make a drift effect, then the group above the steering controller, its value will change. So we can't use this rotation value to drive the rotation of our front controller. Because every time the front controller's rotation value changes, the value of the parent group will change. So what do we need here? We need a value that doesn't change when we rotate the front controller. Let's analyze the hierarchy. This controller is under the front controller as its child. If we look at the hierarchy structure, it's under the back controller. The back controller is under the front controller. So it is under the front controller as its child. And the aim constraint here is a word position. So when we move the front controller, its value will change. That won't work. We need a node above the front controller's hierarchy to find the steering angle and use this angle to drive the front controller. So how do we do this? Here we need to manually add another similar setup. We know the steering controller. The group above it, we did an aim constraint. The driving object is a position above itself, and we use another controller as the up reference object. We need to do the same operation here. We can use this controller directly as the up reference object, because it's also a child under the front controller. We can use it directly. So here we need to create a steering locator and also create an up reference locator. Let's do it. Then group it. This group is 0. Then we need an up position to be the driving object. So let's snap this node to the steering controller's position. Then you will see it's now snapped to this position. As we just said, it needs to be above the front controller and not affected by the front controller. So what is above the front controller? It's the cog controller. So we use the cog controller to apply a parent constraint to this 0 group. Note to keep maintain offset. Because this is a setup done within the shot, so I don't want to put it under the cog controller's hierarchy, because it's not part of the rig. It's just a setup made specifically for this shot. Okay, so here we move the node that will constrain the steering locator up a bit. Next, let's make the up reference object. Then group it. Then snap it to the same position. This is the same operation. Let's copy its name. Then use the locator on top to apply an aim constraint to the locator below. Let's analyze this here. The y-axis is the aim vector, the z-axis is the up vector. Then the up reference object is the locator we just created. Apply an aim constraint. Then use the front locator on the curve to apply a parent constraint to the up reference locator. This way, let's check again. When we enter such a sharp turn, we can see it's about 43 point something degrees here. And the group above our steering controller is the same. But when we rotate the front controller, this locator, because it moves with the cog, it's at the same level as the front controller. So it won't be affected by the front controller. It's still 43 point something degrees here. But the group above the steering controller has become negative 1 point something degrees here. This is the difference between them. So next, we can use this angle to drive the rotation of the front controller to achieve the drifting effect. So what effect do we want? First, before the wheel turns to a certain angle, the car body shouldn't drift. For example, at an angle like this, it won't drift. Only when its angle is too large will it drift. And when it reaches a certain angle, the drift should also have a limit. So here we're going to create a few new attributes. To make it easier for the animator to control, we select the front controller. Add two attributes to it. We'll call it drift min, which is the angle where the drift starts. For example, minimum is 0, maximum is 90, and the default value is 30. Of course, we can adjust this later. Then the corresponding one is drift max. Here, for example, we set it to 60. We can adjust it later too. So next, when this rotation angle enters the range of 30 to 60 degrees, the forward controller will rotate by a certain angle. So how much angle should it rotate? This is also very easy to get. Let's take a look. When the car rotates to a certain angle, look, when this angle is within the minimum value, the front controller shouldn't have any angle change. At this time, the rotation value should be 0 degrees. As the angle increases little by little, when it enters the 30-degree range, now the front controller should start to have a rotation effect. And when it exceeds the maximum value we set, for example 60 degrees, then it should stop rotating further. So let's try connecting it here. First, select the front controller. Add it to the node editor. Then let's see. The angle the front controller can rotate is actually the maximum value minus the minimum value. So here we create a plus minus average node. And set the operation to subtract. Here we use the drift maximum value minus the drift minimum value. This gives us the angle the front controller can rotate. We find the locator created earlier that reads the steering angle. Next, we need to discuss cases because it has positive and negative values. When this value is positive, let's take a look. Moving to this position, when it's positive, the car is turning to the left. And when it's negative, it's turning to the right. So the front controller here will also have different operations. Let's do the positive value case first. We create a remap value node. Rename it to left drift. Connect the locator's rotate Y here. Then its angle range should be on the front controller. The max and min values we set. Then remap it. So when the rotation enters 30 degrees, the front controller starts rotating from 0. And when it reaches 60 degrees, we want it to rotate to the final angle of 60 minus 30. So we connect this subtraction result here. Connect it to the output max attribute. Then we can connect it to the forward controller first to test it. Connect it to its rotate Y. Let's look at the effect now. You will see the wheels don't rotate as noticeably now. Why? Because there is a drifting effect here. Take a look. And when the car returns to a position where it doesn't need to turn so sharply, the front controller's rotation goes back to 0. But of course, there is a problem here now. That is, when the car turns in the other direction, there is no effect. Why? Because this remap value node only handles positive rotation. So next, let's do the other direction. We know the other direction is negative values. So here we need to multiply the max and min values we just had by -1. Only then can it be a negative rotation. Here, let's create a multiply divide node. Then connect all their attributes and change the other input to -1. This way, it becomes the minimum and maximum values for the right side. Same operation here. Connect rotate y here is the input value. The next is output x. That is -30 is input min, and -60 is input max. Then here it's also from 0 to the value we just subtracted. But likewise, we need to multiply by -1. Connect this multiply result to output max. This way, see, it's a drifting effect in completely the opposite direction. If we connect it over here, connect the out value of the right remap value to the front controller's rotate y. Now take a look. When turning right, the car has a drifting effect. But then turning left definitely won't have an effect. So what do? We need to connect them together. Let's check. Now it's rotating to the right. The rotation angle is negative now. The negative value is less than the minimum value, so the output here is 0. And corresponding to the right side, the output here has a value. And if the rotation is positive now, then for the right side, it is also a value outside the minimum value. Because here is 30 to -60, is towards this direction. And if we rotate say 30 degrees, it's to the right of -30. So at this time, its output is the minimum value, which is 0. Because look at this range. -30 is 0, -60 is -30. So when it's 30 degrees is in this direction, so it is 0 at this time. So when we turn to one side, the value on the other side must be 0. And when turning to the other side, the output value in the opposite direction is also 0. So here we can just add their two values together. So let's add them up here. Then connect it over. If you don't understand this setting very well, you can also try using a condition node to connect it. That is, when the rotation value is greater than 0, then output the value of the left remap value node. When it's less than 0, output the right one. Then finally connect the condition node's out color over. That also works. But if you look at the result, you will find that adding them up directly has the same behavior. Okay, so let's check again. When we rotate to the left, I will see a drifting effect here. When we rotate to the right, because this turn is not very sharp on the right, so it may not be that obvious, you will see there is also a certain drifting effect here. And with that, the drifting effect is done. Now let's take a look. The effect of the car moving along the curve is all complete. Finally, we can show the ground again. Let's see how to connect the wheels to the ground. What should we do? The result we want to achieve here is starting from the wheel position, shoot a ray downwards to find the intersection point with the ground. Constrain the wheel controller to this point, thereby ensuring the wheel can stick closely to the ground. But none of Maya's constraint functions can achieve this effect. So here we're going to use another system called mesh. The mesh system in Maya is mainly used for motion graphics. But because its functions are very powerful, in some specific cases, rigging will also use it. So let's do this together. First, we create a locator. Snap it to the position of the front left wheel. We'll use this locator as the starting point to shoot a ray downwards. Let's rename it. Next, use the same method to create locators for the other three wheels. Then we need to move these 4 locators upwards along the y-axis by a certain amount. This is mainly to ensure these locators are always above the ground during the animation. We mentioned earlier, we use the locator as the starting point to shoot a ray downwards. If this locator is below the ground at any frame in the animation, shooting a ray downwards obviously won't have any intersection point with the ground. Then the resulting effect will no longer be correct. So we need to move the 4 locators upwards by a certain amount at the same time. Next, place the 4 locators under the back controller as its children. This way, we can ensure these 4 locators always move with the car. Next, open the node editor. Add the 4 locators to the node editor. Then we're going to create a node. This node is called Mesh Distribute. This node is the starting node in the mesh system. We need to use this node to create the required points in the mesh system to perform subsequent complex operations. Here we rename it. Then select this node. Go to the attribute editor. Here we need to change a few options. First, the point information we need is the front and rear wheels, so change the number to 4. Next is the distribution type. Here we choose initial state. This way it can distribute the corresponding points based on the transform node positions we provide. So here we can place the mouse over the corresponding node, hold down the middle mouse button, and drag it into this add area in the attribute editor. This way we can see this locator is connected to the mesh distribute node. Then we do the same for the other locators. Next, we're going to create another mesh node. This node is called mesh offset. We're going to use this node to shoot rays downwards to find the intersection points with the ground model. Similarly, we rename it. Here we change the mode to closest point on mesh. Then turn off rotation and scale, because we only need the translation information. Next, in the attribute editor, find the closest point on mesh menu. Then change the mode inside to raycast. This way, we can shoot rays downwards. Here we can see an attribute below called ray direction. The default is 0, -1, 0, which is shooting rays vertically downwards. This is the direction we want, so no modifications are needed for it. Then we need to connect the ground model over. So find the ground model in the outliner. Similarly, place the mouse over this node. Hold the middle mouse button, drag it onto this attribute. This way we can see this attribute is connected. Next, inside this mesh distribute node, we need to find the output points attribute. Then connect this attribute to the input points attribute in the mesh offset node. We find the input points attribute, connect them. This way we have found the intersection points of the 4 wheels on the ground. But because all the information is still within the mesh system, we cannot use it directly. So we need to create another mesh node. This node is called mesh breakout. This node is the output node in the mesh system. Through this node, we can convert the point information in the mesh system into translate, rotate, and scale that we are familiar with, thereby controlling each corresponding transform node. We rename it. Then connect the output points of this mesh offset node to the input points of the breakout node. This way, in the output attributes, we can find the translate, rotate, and scale for each output point. Here, we only need translation. Next, let's create 4 more locators. These 4 locators represent in the scene the positions of the intersection points between the wheels and the ground. Later, we can use these 4 locators to constrain the controllers. We duplicate to create locators for the other 3 wheels. Then add these 4 locators to the node editor as well. Next, we need to connect the translation of each output attribute in the mesh breakout node to the translation attribute of the corresponding locator. So what is the order here? The order here is consistent with the order in the mesh distribute node. You can take a look. My order here is front left, front right, back left, back right. So the 4 output attributes in order also correspond to front left, front right, back left, back right. Let's connect them together. The first output should connect to the front left locator. The second output connects to the front right locator. The third connects to the back left. The last one connects to the back right. This way we can see these 4 locators are tightly sticking to the ground. Next, we can clear the node editor and close it. Then use these 4 locators to constrain each wheel's ground controller respectively. We select the front left locator. Select the front left ground controller, then apply a point constraint to them. Note here to turn off maintain offset, because we need the wheel to stick tightly to the ground. Also note here we only constrain the y-axis, because the x-axis and z-axis are already locked, and we also don't want the wheel to have any strange offsets on the x and z-axis. So in the options, we'll only select the y-axis. This way we can see this wheel is sticking tightly to the ground. Next, do the same operation for the other wheels. This way we can see the 4 wheels. Because of the settings just now, always stay on top of the ground. If we drag the timeline, we can see on the uneven ground, the wheels are always above the ground. And because in the car rig, the up and down movement of the car body and wheels has a linked effect. So when we play the animation, we can see the car body will also produce corresponding swaying effects based on the different wheel positions. This way, our car animation setup is complete.